Hey everyone and welcome back to PrepFusion. So today we'll be starting the lecture 9, that is basically the analysis of parameter of second order underdamped system by varying the poles, right? So in the previous lecture what we did, we simply did the assignment solutions, right? So I hope you understood the solutions. So before starting the lecture, right, what I will say is like you try to analyze the conditions by yourself. Okay, first I will write what things are varying and what things are constant, so you try to analyze those by yourself, pause the video, then you see my solutions, how am I analyzing and how am I comparing the time domain parameters, basically varying the poles, right? Okay, so let's start the lecture. Okay, so how can I vary my poles? So let me draw the sigma j omega plane. So if I draw my sigma j omega plane, right, so topic is first how can I vary my poles. Okay, so here I have my two axes basically. Okay, sigma and j omega, right? Now let's say my poles are lying somewhere around here. They are complex conjugate because this is a underdamped system, so they are lying somewhere around here. Okay, so how can I vary my pole? So basically what are the parameters, like what are the things that define this pole location? One is this j omega d. Okay, this one defines, and another one is my zeta omega n. Is there anything else? So there is also this angle, right? This angle theta. This can also define my pole. So omega n I can write in terms of zeta and omega d. Okay, that I can write. Okay, so what I'll do, so what are my variables here? I have three variables. Okay, one thing is, okay, because this theta will also vary. I will when I will do the analysis, there you will understand why this theta is also a variable, right? So my variables are my zeta, omega d and theta. Okay, these three are my variables. These three parameters which I will vary to vary the location of the poles. By varying these three parameters, the location of the poles I can vary, right? So yeah, let's see how does that happen. Okay, let's take the first case where my like condition first. Okay, condition 1 where my this what do you call this zeta omega n, right? This location is fixed, zeta omega n is fixed. Okay, now if my zeta omega n is fixed, the other two will vary. So let's see. So my zeta omega n is fixed, right? Or let's say yeah, it's fixed. So my zeta omega n is fixed. Then how will the location of poles vary? So I will copy this one. Okay, now this part is fixed, right? This part is fixed. So what will vary? So obviously my omega d can vary. So if omega d is varying, then I can move above, but I cannot move this part. So I can only move in this direction, right? In this direction. So what will change? My angle will keep on increasing. Okay, my angle will keep on increasing. Like this side angle will keep on increasing and my height will keep on increasing. So what is happening? I am doing a vertical movement, right? Vertical movement of poles. So I am doing a vertical movement of poles, right? So this is known as the vertical movement of poles. So okay, so this is the vertical movement of poles basically. So what will vary? My omega d and theta will vary. So basically if I measure the theta from here, right, theta is increasing, right? So what I will do, like here, so let me draw this in different color actually. let's say this one was my initial, okay, this one was my initial. Okay, why is this keep on going in other areas? Okay, no, not this one. Yeah, this one was my initial theta 1, right? Now let's say this is another like a next variation for another location, second location of the pole. This is my theta 2, okay, and I have third pole. Okay, I will choose 3 poles and compare those 3 poles and the time domain parameters. So this third pole, right? Okay, sorry, third pole is this one. So angle, as you can see, is keeping on increasing, right? So this is my third pole, okay, theta 3. Okay, so this is my theta 3. Okay, so now I will compare these 3, okay, with other ones. So also I will write the damping frequency also, how it is varying. So here, as I can see, damping frequency is increasing, right? The third pole has the highest damping frequency. So this will be my j omega d1, okay, and this will be my, okay, let me put this j omega above. This will be my j omega d3, okay. So these 3 are there, okay. So like now I can compare. So what is the first thing that I notice? So let's compare first. What is the first thing that I notice? First thing that I notice is my omega d3 is the highest, right? So my omega d3 is greater than omega d2 is greater than omega d1, okay. So omega d3 is highest in this case, okay. This is the first thing. Next, theta I can compare. So my theta, right, my theta, okay, let me write this as like 1, okay, sorry, and this is my omega d3, and like so what is my theta? So theta is increasing also. So this is theta 1, this is theta 2, and this is theta 3, okay. Now what is my zeta, right? So what is my zeta? Zeta is basically will be inversely proportional to the theta, right? If theta is increasing, then, okay, sorry, one thing I did wrong. This will be theta 2, theta 3, theta, sorry. So this is theta 3, theta 2, theta 1. So if my theta is increasing, my zeta will reduce, right? Zeta will reduce. So my zeta 3 will be less than zeta 2 will be less than zeta 1, right? Why? Because we already know that zeta is inversely proportional to theta, because like it is cos theta, right? Cos theta. So I mean zeta equals to cos theta. So cos theta is like inversely proportional to theta. That's why. Okay. So that is basically my zeta. So now let's solve for the other time domain parameters. So one thing I can do is compare the time constants, right? Time constants of each of these. So my fourth parameter, right, is the time constant. So what is my time constant equals to? Time constant equals to simply 1 by zeta omega n, right? So it is simply 1 by zeta omega n. Now this is constant, right? This location is constant, okay. I'm not varying my zeta omega n, okay. So I should write here like it is function of zeta, but I should also write here like this location, right? I should write here this is function of zeta omega n. That is one mistake I did. This will be function of zeta omega n, not only like not only zeta, because what can vary my pole location? One is the x-axis. So x, along x I have this zeta omega n. Along y-axis what is there? Omega d. And obviously along the angle also I can vary, right? This is theta, okay. So yeah, these 3 things, okay. That's why that was one mistake on my part. So the zeta omega n, so tau is inversely proportional to the zeta omega n, and this is constant, right? Now if this is constant, my tau 1 will be equals to tau 2 will be equals to tau 3, okay. So this is my tau. So what is my fifth parameter? Let's say I want to find the peak time, right? Peak time, TP. So what was my peak time formula? It was pi upon omega d, right? Pi upon omega d. This was the formula for peak time. Now what is happening to my omega d? So my omega d, right, as you can see, omega d is increasing, right? So if my omega d is increasing, then my peak time will reduce, right? So with each pole my peak time is reducing. So this is equals to TP3 will be less than TP2 will be less than TP1. Okay, so it will be less than that. Okay, so that is basically my peak time. And now, right, basically what is the, let's say I want to find my settling time. So settling time will also be equal, okay, because it is photon only. So T is settling, right, equals to photon only, hence my settling time is constant. So simply, right, it is equals to T settling 1 is equals to T settling 2 is equals to T settling 3. Okay, so these are same. Now what is basically other parameters? Let's say I want to find for the delay time, which is the worst one. Okay, which is the worst one. So for delay time, right, you usually do the delay time as a function of rise time only. I mean, you do one thing, that delay time is proportional to the rise time. Okay, if for some reason you're confused. So what is delay time? Delay time equals to that weird formula 1 plus 0.7 zeta divided by omega n. Now what is happening to zeta? Zeta is reducing, right? Zeta is reducing. Okay, but what is happening to omega n? Omega n will increase. Why? Because zeta omega n is constant. From here also you can understand, or you apply the simple formula of omega d equals to omega n 1 under root 1 minus zeta square. That also you can do. Anything you can do, whatever suits you. But the simple thing is that what I know, my zeta is increasing and my zeta omega n is constant, right? Is constant. Hence my omega n needs to reduce. Sorry, zeta is not increase. Sorry, zeta is reducing. Sorry, zeta is reducing. So my zeta omega n is constant. So my omega n needs to increase, right? Omega n needs to increase. Hence this needs to increase, right? As zeta is reducing and zeta omega n is constant. So yeah, so omega n will increase. So what do I observe here is that omega n is increased and this zeta is reducing. Okay, so this overall numerator is reducing and denominator is increasing. What happens? So numerator from 2 it becomes 1 and denominator from 2 it becomes 4. So obviously the whole value reduces. So my delay time is reducing. So my TD3 will be less than PD2 will be less than TD1. Okay, so this will be about my delay time. Okay, so now let's solve for the peak time. Okay, not solve for the peak time, not solve for the peak time. Now let's solve for the rise time. Okay, rise time, what parameter is this? This is the 8th parameter, right? Rise time. So what is the formula of rise? TR, right? TR was simply pi minus theta by omega d. I hope you remember. Now what is happening to my theta? So theta is increasing, omega d is also increasing. So how will you find? So but what is the main thing here? Theta is increasing, that is fine. Theta is increasing, omega d is also increasing. But if theta is increasing, pi minus theta will reduce. So this whole thing will reduce, right? If theta is increasing, this whole thing will reduce. Then what will happen? Then basically, right, then basically the numerator is again reducing and omega d is increasing. So again rise time will also reduce. So basically rise time and delay time are basically proportional to each other. So if rise time increases, delay time will also increase, and if delay time reduces, rise time will also decrease. So and vice versa. So my rise time will basically reduce. Okay, so TR3 will be less than TR2 will be less than TR1. Okay, so these are the time domain parameters. So is there anything else left? Yes, there is one more parameter, that is the, what is it? Tell me, what is it? It is the maximum peak overshoot, right? So maximum peak overshoot. So what is the formula of maximum peak overshoot? It is basically e raised to power minus pi cot theta. Okay, it is basically e raised to power minus pi cot theta. So if it is equals to e raised to power minus pi cot theta, then what is happening to theta? Okay, my theta is reducing, sorry, increasing. Theta is increasing. If theta is increasing, then cot theta will what? Reduce, right? Cot theta is what? Cos theta by sin theta. So if it is cos theta by sin theta, we know for cos theta, theta increases, cos theta reduces. So it is a numerator, it will reduce, and denominator is increasing. Hence, basically, right? So like this will reduce, right? This will reduce. Okay. Now, if this is reducing, then my exponential term is reducing, right? Hence, basically the negative exponential. Let me write it like this one. So e raised to power pi cot theta. Okay. If cot theta is reducing, this will also reduce. Okay. This will also reduce. Okay. Something to the power is reducing. That power will also reduce if it is positive. So I made it converted to positive, right? So to better explain it to you. So this is reducing, the denominator is reducing, numerator is constant, then what will happen? The whole thing will increase, right? Hence my MPO will increase. Okay, my MPO will increase. So what I can write, MPO 3 will be greater than MPO 2 will be greater than MPO 1. Okay, so this is basically my relation, right, for maximum peak overshoot. So from this, right, I can plot the unit step response from all this information. So what is this information is very important. My third peak overshoot will be greater than the second peak overshoot will be greater than the first. I mean, not the second peak overshoot, but for the third location of the pole, and for the second location of the pole, and for the first, like the 3 poles we have, right? 3 different systems we have. Okay, so yeah, so I have plotted this one. So from here you can understand that initially the third system has the most MPO, then the second system has the second most MPO, and the first one has the least one, right? So it is reducing, okay, according to system. Also, what do we notice? We notice that the each has different rise time and delay time. So it is reaching much faster. So rise time is much faster for this one, but its MPO is much higher. So here also we can observe that MPO and rise time are inverse of each other. Okay, so if MPO is increasing, then rise time will decrease, right? But yeah, there is trade-off, right? I'm getting too much overshoot, so that we have to see, right? That we have to see. So MPO is the problem. So that is one thing. And what else can we see? So this settling time, right? So it's all of them settle almost at same time. Okay, this is also I noticed that zeta omega and all of them settle at almost same time, because none of them has settled yet. Okay, so all of them will settle at almost same time. That one we can notice. And peak time, I can see peak time is least for this one. So obviously, yeah, peak time, all the time domain parameters will be best for this one except the MPO. That is the only issue, right? So it has more overshoot. So that trade-off we have to think of, okay, as a control engineer. What things we need to choose. Okay, so yeah, that was it. So for the most balanced one, right, obviously you can choose 2, right? 2 you can choose. It has lesser MPO and okayish time domain response, right? Rise time, delay time, all those things. So according to that you can choose. So yeah, this was the step response of second order underdamped system where omega d and theta were variable, or you can say that my zeta omega n is constant. So I will write here my zeta omega n is constant. Zeta omega n is constant. Okay, so yeah, now let's go for the second condition. So what is the second condition? Condition 2, right? What is the second condition? Second condition is basically where I vary my zeta omega n, okay, where I vary my zeta omega n this time. Okay, first I varied that y-axis, basically omega d. Now I will vary my zeta omega n. So if I vary my zeta omega n, what is constant? My omega d is constant, right? So this time, right, my omega d I will keep as constant. Okay, okay, if my omega d is constant, and like this is my omega d basically, but my zeta omega n is varying. According to that, the theta will also vary, right? Let's see. So let's say I have a pole up over here, 2 poles, and poles up over here, and poles up over here. Okay, So this is actually j omega d, and this is also minus j omega d. Did I put the poles in the previous case? Yeah, I put the poles, right? Yeah, like there will be here, I didn't write it here, there will basically this is so these are these things, okay, and this is j omega d1. Okay, so yeah, yeah, this one were these poles. Now these are different locations, okay. So this is one location, this is one location, this is one location. So this is where did I go? So this is basically minus zeta omega n, okay, for the first one, okay, minus, let's say, zeta omega n, what you can say, yeah, zeta omega n 1, okay, this is the first product, okay, and now this is the second product, minus zeta omega n 2, and this is the third one, okay. So I'm basically varying both of them. I'm not telling you the exact value. Exact value we can know from theta itself. From theta I can tell that what is happening to zeta, okay. So this is omega n 3, okay. So or like I can write this like this one only, don't need to write it in bracket, okay. So this is omega n 1, okay, I need to write it in different colors, actually I forgot. So this one will be zeta 2 omega n 2 and this one is minus zeta 3 omega n 3, okay. So yeah, these are these three pole locations. So now, right, what is happening to the angle? So the angle basically is like this one. So this is the first angle, so this is my theta, right, theta 1, let's say theta 1, and what is happening to the second angle? Theta 2, and what is happening to the third angle? Theta 3, right, this is theta 3. So so yeah, this is my third angle basically. So now let's compare, right, let's compare. So first thing, what we know, what is the known condition here, that omega d is constant. So okay, I should write this as second. Omega d is constant, so omega d1 equals to omega d2 equals to omega d3, right, okay. So my omega d is constant, so my omega d is constant, what will be my second? So theta, right, now we'll see theta. So what I can see is that if I'm going here, so it is visible that my theta is reducing, right, theta is reducing, okay. So my theta 1 will be less, okay, greater than theta 2, greater than theta 3, okay. Or I can write this in the reverse direction because that will be better to understand, okay. So I will write this like this one, theta 3 will be less than theta 1 will be less, oh sorry, theta 2 will be less than theta 1, okay. So this is about the theta, okay. So now what about the zeta? What is about the zeta? So zeta, right, so if theta is reducing, zeta will increase. So zeta, it is inverse relation, right, it follows inverse relation, zeta 3 greater than zeta 2 greater than zeta 1, okay. So zeta is increasing. Now, right, what about omega n? What about omega n? So like this zeta omega n product is increasing, right, okay. So this is also increasing. So like, okay, from not from here, I can't say, okay, I can't say from here, but what do you know? Omega d is constant, so omega d is constant, right. So what is omega d equals to? It is omega n under root 1 minus zeta square, right? So if zeta is increasing, zeta square will increase, okay, but 1 minus zeta square will reduce, right? Okay, so this whole thing will reduce, but this is constant, so this whole thing is reducing, but this is constant, right? This is constant. Now if this is constant, then what will happen? This will increase, okay. This will increase, so like this has to be constant, right? This has to be constant. So yeah, there is basically omega n into under root 1 minus zeta square, okay. So yeah, so omega n will increase, so omega n3 will be greater than omega n2 will be greater than omega n1, okay. So these three will increase. Now let's evaluate for the maximum peak overshoot, right? So anything we can evaluate, let's evaluate for the maximum peak overshoot. So MPO, right? MPO, if I evaluate, MPO, okay, I have lost, sorry. E raised to minus pi cot theta, okay. MPO is e raised to minus pi cot theta. So is MPO is e raised to minus pi cot theta, then what is happening to theta? Theta is this time reducing, okay. Theta is reducing, as you can see, right? So it will be just opposite of previous one. So if theta reduces, my cot theta will increase, okay. If my cot theta increases, then what will happen? My e raised to minus pi cot theta will also reduce, right? Because something negative power is increasing, so obviously this whole thing will reduce. So e raised to minus pi cot theta will reduce, right? So that will reduce. So now, right now, what does that mean? My MPO is reducing, okay. My MPO is reducing, so my MPO3 will be less than MPO2 will be less than MPO1, okay. My MPO1 will have the maximum peak overshoot, but as you know, right, the rise time and MPO follow the inverse relationship, so rise time will just be opposite of this one. So okay, this is really third parameter. No, I have done fourth, okay. This is the fifth parameter, so this one will be the sixth one. Okay, so this one is the sixth one, okay. So now, right now, let's do the rise time. So like I already know it follows inverse relationships, so MPO 1 will be basically, I mean, sorry, what MPO, so TR3 will be least, no sorry, TR3 will be maximum, okay, and TR1 will be least one. So but still, pi minus theta upon omega t, this is my TR, right? So what is happening? My theta is reducing, right? Theta is reducing, okay, and my omega d is constant. So if theta is reducing, then this whole thing will increase, right? So if whole thing is increasing, my rise time will also increase. So my TR3 will be greater than TR2 will be greater than TR1, okay. So this is about my rise time, okay. So yeah, now what about the time constant? Tau is basically 1 upon zeta omega n, right? Now my zeta omega n is increasing, right? Zeta omega n is increasing, okay. So if my zeta omega n is increasing, then what will happen? Basically my tau will reduce, so tau 3 is less than tau 2 is less than tau 1, okay. So that is basically my zeta omega n. Now what about settling time? Settling time is directly proportional to tau only, so T settling, okay, is equal to 4 tau only, okay. So it is basically T settling 3 is less than T settling 2 is less than T settling 1, okay. So this is what basically is t settling equals to. So let's now solve for the another parameter. For the delay time we can solve. Okay, for the rise time we can solve. Okay, rise time we already did. Okay, delay time we can solve, right? What is the delay time? So delay time is again directly proportional to the rise time. Okay, if you don't understand, so what I will suggest is just do delay time directly proportional to rise time. So delay time, because it's just we'll just waste our time analyzing it. So delay time is directly proportional to rise time, so rise time is increasing, so delay time will also increase, right? Okay, so this is basically what delay time and rise time is. Now basically, right, certain time I did. Okay, so because this this analysis will be a bit difficult if you directly solve it from formula, so you can use this method. Okay, else like solving from the derivation, like the actual formula of delay time, it will be difficult, because delay time itself is an approximate formula. Okay, it is not an actual formula. I mean, it is basically, it varies, right? So did I did all the parameters? Yeah, 9 parameters I did. Okay, fine. So yeah, okay, yeah, this is the drawing basically. Okay, where, like, let me say that where omega d is constant. So let's check what things are okay with this. So here what do I see? I see that my MPO, right, MPO is reducing. Okay, so this is the first one, and it is reducing. So for the third one, it is the least one. So third one is the least one, right? Third one is the least one. Here my third one has the least MPO. Okay, so what else we can see? We can see, okay, did I calculate the peak time? Okay, I forgot to calculate the peak time actually. Okay, I missed one parameter, but still I got 9 parameters. How previous parameter I didn't got one? Okay, I don't know. So what will be peak time? So peak time, right, peak time is pi upon omega d, right? And my omega d is constant, so my peak time will be tp1 equals to tp2 equals to tp3, right? The previous one, what did I miss? This is this one. Okay, fine. Did I miss? Okay, I missed this one, that omega zeta n equals to that parameter. Omega zeta n is fixed, that I missed. Okay, else all the parameters are done. So peak time is fixed for this one. So if my peak time is fixed, that means each peak, right, that I am getting reaching at is fixed. Each peak that I am reaching is fixed. That's why all of them reach the peak at the same time, but they have different rise time and delay time, because like this is rising much faster. Okay, much faster to much higher level at the same time. Okay, that's why this its rise time is lesser, and this has more rise time, and this has the most rise time, right? That's why delay time is also more and rise time is also more. Okay, so yeah, from there you can understand, but the main point that you do is check the what parameters are same. So my peak time is same, so this will be same, and my MPO is more for the first system. So yeah, it is more for the first system. So in this case, right, in this case, which system will be best for me? I think the best system will be this one, right? But the problem is not this one, because again this has also another problem. MPO is less, but the rise time and delay time are too much time it takes to rise, right? So that is the issue. Then I will have to again choose 2. Okay, for the most balanced one. Okay, so yeah, like this one you can understand. And what about settling time, all those things? So settling time, right, settle time is reducing for the third system. So this one, this third system I am seeing is settling much more faster, right? And this second system and this second system is settling before after that, and this first system still hasn't settled, right? It will take time. Okay, so yeah, that was about the settling time and all those things. So now let's go for the third variation. What is the third variation? Third variation is basically where my theta is constant. I keep my theta constant. Okay, theta equals constant. So my theta is constant, then what will happen again, right? So let me, can I draw this? Let me draw this anyways. So my theta is constant, what will happen? So one pole will lie over here, again my theta is constant. I can't keep my pole over here because theta will reduce. I can keep my pole over here because theta will reduce. I can keep my pole over here. Okay, so okay, one thing I wrote to, like, forgot to wrote here is that this is the what do you say, this is the horizontal movement, right? Horizontal movement. So this is the horizontal movement of pole. Okay, movement of pole. And this one is the vertical movement of poles. Okay, yeah, that I wrote here. So if I got to wrote here actually vertical movement of, so this is fine. So for this one, right, this one, if I can keep it along this one, okay, keeping the angle constant, like 3 poles I will keep, right? This one, okay, this one will be another pole, this one will be another pole, okay, and this one will be another pole, and yeah, this one is basically this one. So basically, right, what will be this angle? This angle is theta 1. I mean not theta 1, this is theta only, this is constant only. So the omega d and omega zeta omega n values will change. So let me name this one. So this one is j omega d, okay, too much thing, yeah, j omega d1, and this one is j omega sorry, d1 only, minus j omega d1. Okay, okay, and what is this one? This one is basically, look, I need to again increase the height of this one. Increase the height of this one. This one is basically minus j omega d2, and this is plus j omega d2, right? And what is this? Minus j omega d3, and this is plus j omega d3. Okay, so these are my basically pole locations. Okay, so now what I will do is basically that this theta is constant. So the first thing that I know, what do I know? What do I know? I know my theta is theta 1 equals to theta 2 equals to theta 3 equals to theta only. It is constant, right? Now what is varying? My omega d1 is also increasing, and my zeta omega n also increasing. So I should write here, I forgot to wrote here that this is my zeta 1 omega n1, this is my zeta 2 omega n2, and this is my zeta 3 omega n3. Okay, so these are my things. So yeah, so right, what is happening to, so my zeta is constant because theta is constant, right? So I should write here zeta only. So I will not write here zeta, I will write here only that if my theta is constant, so my zeta 1 equals to zeta 2 equals to zeta 3, as my theta is constant. So MPO will also be constant, theta is constant. So this one I can write. Why? Because my theta is constant, right? That's why. Now what is about omega d? Omega d will obviously be increased, right? Omega d will obviously increase. So omega d3, okay, will be greater than omega d2, will be greater than omega d1. Okay, so yeah, those will increase. Now what about my time domain parameters? So basically, what about my time constant? So my time constant, right? So time constant is what? 1 upon zeta omega n, right? So time constant is 1 upon zeta omega n. Now my zeta is constant, but what is happening to my omega n? So here also I can write, before writing the time constant parameter, what about my omega n? So what is my omega n? Omega n is basically, okay, let me keep this here. Omega n is basically equals to omega d by 1 by 1 minus zeta square. Okay, so this is my omega n. So zeta is constant, omega d is increasing, right? Omega d is increasing, zeta is constant, so omega n will also obviously increase, because here it has to increase, right? Because zeta is constant, so it is going in this direction, so omega n has to also increase, so omega n will increase. So what will be the variation of omega n? So this, right, I need to put this, delete this over here. So my omega n, right, omega n3 is greater than omega n2 is greater than omega n omega n1. Okay, so these are like this one only. Okay, so okay, so now let's do for the time constant. So as I can see, right, omega n is increasing, hence my tau will reduce. From here you can see also that what is tau? Tau is inverse of the zeta omega n, right? So here this is increasing, right? So this is the inverse will decrease. This is increasing in the x-axis direction, so inverse will decrease. From there also you can understand. So so my fifth one is tau. Tau is 1 over zeta omega n, right? So tau is 1 over zeta omega n. Okay, so my tau, this is increasing, right? So my tau will reducing. Okay, so my tau 3 will be less than tau 2 will be less than tau 1. So it is directly proportional to a settling time. Okay, so it is directly proportional to the settling time, then my settling time will also reduce, right? Settling 3 less than t, settling 2 less than t, settling 1. Okay, so this will further reduce. Okay, now what about my delay time? What about my delay time? So about my delay time, right? So delay time, again I will choose it directly proportional to rise time. So first I will find rise time. Okay, what is my t rise? Equals to t rise, right? Again that formula, pi minus theta by omega d. So omega d is increasing, okay, and theta is constant. This is constant. Okay, omega d is increasing, so tr will reduce. So tr3 will be less than tr2 will be less than tr1. Similarly, if you calculate for this what do you say, delay time, right? Delay time I will assume it is proportional to the rise time, or you put it here in the formula. This time it will work, previous case it won't work. 1 plus 0.7 zeta equals to omega, right? So this is basically divided by omega. So what is happening? Zeta is constant only, but my omega is increasing. So td will reduce. So my td 3 less than td2 less than td1. Okay, so this is basically my td equals to. So now what about my MPO, right? What about my MPO? MPO will be constant as theta is constant. So this is my 9th parameter, basically MPO equals to e raised to power minus pi cot theta. Now MPO will be constant because theta is constant, right? Theta constant, MPO will also be constant. Okay, so MPO 1 will be equals to MPO 2 will be equals to MPO 3. Okay, this is just the basic analysis. So what you should have done, I should have told this actually at the start, that you pause my video and do all the compare all the parameters by yourself, then you recheck your answer, right? So yeah, I missed that part. So like, you should have done it like that only. Okay, whenever you get the chance, right, whenever I solve something, you pause the video, you solve it by yourself, then check whether you're doing it correctly or not. From there you will understand that whether you understood the concept or not previously, right? Okay, so it is very important. So all this will be equal. One more parameter is there, that is the peak time, right? The 10th parameter is the peak time. So what is the peak time? Again, it is pi by omega d. If it is pi by omega d, then my omega d is increasing. Okay, omega d is increasing, and this one will reduce, this one will reduce, right? So yeah, so if the peak time is reducing, that means my TP3 will be less than TP2 will be less than TP1. Okay, so this is how basically my parameters will vary. Okay, so now I will obviously I have drawn the thing. Okay, let me delete this one. Let me say that this time my theta is constant. Okay, so what are you noticing? The first thing I notice is my peak overshoot are same, so my response will lie within certain band only. Okay, so my peak overshoots will be same. Okay, what other thing do I see? The other thing that I see is that my peak time will reduce, right? So for the third system, I will have least peak time. So the third system will reach peak early. It will have less settling time, because here also zeta omega n, okay, t settling is less, my tau is less, my rise time is less, my delay time is less, so it will reach there faster. Okay, so for and everything is less, and my peak overshoot for all the three systems are same. So here I can directly say that my third system will give me the best performance, right? Third system, I should not write it here, actually I should write here only. I can directly compare, because peak overshoot for all of them are same, but the time domain parameters, right, the rise time, delay time, peak time, all those are less, right? It is reaching faster. Okay, settling time is also less, so it is settling faster. So I can directly say my third system will be best for performance. Third system has best performance. Okay, so this is my third system basically. So this one I can tell directly. So yeah, I think that that one is it for this lecture. So let me this lecture is already gone long, so I won't I will just give you a quick recap. Okay, I will just give you a quick recap that what we did. First, we understood that what things can vary the pole. The x-axis can vary, the y-axis can vary. Okay, and due to variation of x and y, if I due to variation of both x and y, my angle will be constant. Okay, my angle can also vary, right, keeping one of them constant. So that's why I chose these three parameters. Okay, these three parameters I chose. Then what we did the vertical movement, that where my omega d was varying. Okay, and the other that zeta omega n was constant. Due to that, as zeta omega n is constant, my theta is also varying, right? And we compare the parameters. So this you should compare it by yourself, not seeing my solution. Okay, then you see that whether you are correct or not. Okay, so like one thing to keep in mind is that the rise time will be proportional to the delay time, or delay time will be proportional to the rise time, because calculating it using this method, right, is a bit difficult. Okay, that's why. So yeah, then we plotted. Okay, so we plotted the response. Then we did the horizontal movement of poles, which means basically my zeta omega n is increasing and my vertical axis are fixed, right? So I am moving in the horizontal direction. That's why it is known as horizontal movement of poles. Next, what we did, like here also I won't be able to tell which one is best, right? Because something has more MPO but it has less rise time. In the previous case also, it has more MPO but it has less rise time. So here also I won't be able to say, but one thing I will be able to say, that this has so much lesser rise time than this one, so maybe I will choose this one. Okay, maybe I'll choose the third one, but not surely, right? But in this case, right, so in this case, where theta is constant, this is known as the diagonal movement of poles. This is known as the diagonal movement of poles, right? So this is a diagonal movement of poles. Now, right, for this case, my zeta is constant because theta is constant, but my omega n is increasing and my omega d is increasing, right? So I compare the values, but here clearly I can see that third system has the same peak overshoot and it has a less rise time, less settling time, everything less, right? So the third system is best in terms of performance. Okay, so that's why I will choose the third system here. So like this one also, you can compare systems and you can choose which system to choose and which system to not choose. So yeah, this will be the end of this lecture. Thank you for watching.